Okay, let me give you guys some more examples of proportionality. Imagine you're going into space. You're going to bring a small die with you, and you're going to bring a small stone with you. Now, in space, if you have an object, or let's say of mass capital M, and another object, the stone in our case, small m. Now, if you leave them near to each other, after about half an hour, they will come together, and that's what this formula is saying. It's saying that when you have an object of mass m and another object of another mass small m, there's a force that exists between them, and it is dependent on the distance that separates the two. So the further they are away from each other, the weaker the force, and then the nearer they are, the stronger the force. Well, this formula here tells you the relationship between the mass here, and you also have to take into account the distance separating the two masses. So it's just like you and the Earth. You see, the Earth has a mass. You here, standing on Earth, has a mass let's say small m, and then well, that's what in effect that's what gravity is. It's like a mass. You have a mass here and a mass here. They want to come together. Now, in this video, we're going to investigate what happens when you change the distance that separates the two objects. So here, let's say the distance that separates the two objects here is r here. So there is a force that exists between them. But what happens to the force when we double the distance here? Okay, but before we do that, let's just look at something. Here you've been given this formula here. We can visualize this as, well, here you've got a number here. G is just a number. It happens to be a really small number. It's a constant. It doesn't change. And then you've got that number multiplying this fraction here. So it gets multiplied to the top. So you can imagine it as this: capital G times capital M times M over R squared. Okay, now I can visualize this as being in a bubble here, and I'm just gonna pull out the bubble. So it becomes this. Hang on, G capital M M. So this here exists in a bubble, and then this gets multiplied with this. Hang on, 1 over r squared. I am allowed to do this because if you work in reverse, here you've got a number timesing a fraction, so you multiply it to the top. So from here I am allowed to jump to here. Okay, but here's the thing. I am now so this whole thing here is just a number. It's just a number that doesn't change. In our case, we don't really care because the mass of the die here, which is capital M, doesn't change, and the mass of the stone here doesn't change. And this number capital G here is just a constant. It doesn't change. So it's just the whole thing here is just a number. So I am allowed to do this here. This whole thing here becomes this. It's just a number that doesn't really change. So I'm going to give it a new name, K. Okay, it's just a number that I don't really care about. It's just a number that doesn't change, and I don't really care about it. So I'm just going to call it a new name, K. All right. So it just makes it simpler. So now it becomes this. So K is currently multiplying a fraction, so it gets multiplied to the top. So it becomes K over R squared. Okay, so F here equals this. Now, in the past, if I were to say, oh, F, the force, let's just say something. Okay, let's call it Y then. In the past, if I were to say Y is inversely proportional to X, then you can, from here you can immediately jump to Y equals K over X. Okay, so now we are working in reverse. I've got this thing here that's saying Y equals this thing here. So I can work in reverse and say that, oh, Y is inversely proportional. Well, here currently this thing here is the same as this thing here. Okay, so currently I am here at the moment. I am allowed to say, oh, so sorry, hang on. Currently, this thing here is this thing here at the moment. Okay, hang on. We are here at the moment. So which is this thing here? We've got a force equals a number that we don't care about over r squared. Now from here we can work in reverse, just like up here. We can say, oh, by the way, F is inversely proportional to, instead of R, we've got R squared. So here we can jump to this. Oops, sorry, hang on. Whoops. So here we can say this. Hang on, sorry. So instead of saying 1 over R, we're saying force is inversely proportional to the square of the distance. Okay, so from here we are allowed to jump to here because when we were here we can jump to here. So now we are working reverse. We are here. We can actually say, oh, y is inversely proportional to the square of the distance. So what that means is, look what happens here. Hang on. So we can say this, and we can say this as well. Okay, hang on. Let's go back to the original thing. So let's clear this. Okay. So currently, the force that exists between them equals this. F equals a number that we don't care about over r squared. Okay. Now, so this is our current situation. Our current situation. Our current situation, the force equals this. Now let's double the distance. So our new situation here, the distance now is 2r. So let's put this into that formula, into this r here, because here let's change this to old now. Our old situation, the distance is r. Now our new situation, the distance now is 2r, and you've got to put that into the r and then square it. So look at this here. F here equals a number that we don't care about over, now so here you've got r, and then you've got to square it. Okay, now the distance, our distance now is 2r, so we're going to put 2r into here. Okay, so this becomes now let's just work out this bit here, this bubble at the bottom. What's 2r squared? 2r squared means 2r times 2r. So you would get a number times a number, letter times a letter. So this becomes 4r squared. Okay, so this thing here, F, equals a number that we don't care about over 4r squared. Okay, so now we can write it like this. We can write it like this. We can take the 4 out, but the thing is, when you take the 4 out, you have to do this. You have to do this here. Hang on, k over r squared. Okay, you have to do it as 1 over 4. You can't do it 4, because if you just write 4, if you just write 4, it's just going to get multiplied to the top. It doesn't make sense. You see, you have to write it as a fraction, because top times top, that will give you k. That will give you this thing here. And then bottom times bottom, then that will give you 4r squared. My point is that when we double the distance, the force that exists between them is given by this here. Now, if you look at our old situation here, the force that exists between them is given by k over r squared. Now look at the new situation. You see, k over r squared this is our old one. Now our new situation becomes 1 over 4 times the old situation here. So what that means is when we double the distance, a new force, this is our new force. Our old force was this, F equals k over r squared. You see, this bit here is exactly the same as this thing here. But the thing is, our new force is a quarter of that. So you can imagine it as getting our old force and dividing it by 4. That's what times a quarter means, dividing by 4. So you can say that doubling the distance will actually, well, you've got to divide the old force by 4, meaning that the strength, the force will be 4 times less. Okay, because of this thing here. Okay, so hang on. So let's go back to this here. So if you double the distance, you will actually decrease the force by 4 times. So yeah, you will decrease the force by 4 times. Now, let's say if you half the distance, so now R is R over 2. Now, if you put this R over 2 into that thing there, hang on. So before it was, our old system is this: F equals K over R squared. Now, if you want to investigate what happens when you half the distance here, well, put this thing into the R here, so it becomes this. K. Well, what's R squared here? Well, if you put this thing into this bubble here, so it's like this. So it's like this: R over 2, because our distance is now half. So what's R over 2? What's R over 2 squared? You see, R over 2 squared equals R over 2 times R over times R over 2 here. That equals R squared over 4. Okay, so this thing here becomes this, R squared over 4. So whenever you have a fraction within a fraction, you've got to you've got to visualize it like this: K divided by R squared over 4. Now turn this K into a fraction, so it becomes this: K over R, so here you've got K over 1. K over 1. Turn the K into a fraction. So here you've got a fraction dividing another fraction. So you hang on. So here when you've got a fraction divided by another fraction, you would keep this the same, but then you times the reciprocal. This is with fractions here. When you have this here over this, well, you keep this the same, and then you times the reciprocal of this. So this will be this. You keep the K the same, well, this thing here the same, keep this the same, and then you times the reciprocal of this, so this will become this, R squared. So now it's just top times top, bottom times bottom. So hang on, this will become 4K over R squared. Now look at this here, hang on. So now let's pull out the 4, so it becomes 4 times K over R squared. You see, our old system, F equals K over R squared. Now, when we half the size, our new distance is R over 2, and then when we half the distance, RF becomes this whole thing here. Okay. Now, if you look at this here, this is our old force here. But when you half the distance, then you put this 4 here. You see, this is the force of our old system. And then our new force will be, look, times 4. So it's going to be 4 times the strength of our old force. This is our old force here. So what this means is that, when you half the distance between them, the force will become 4 times stronger. So my point is that from this formula here, you can actually say, oh, the force that exists between them is inversely proportional to the square of the distance. Okay, that's what it means. Okay.